as we saw in class, the human hopper game was certainly not a fair game. Upon first inspection, many of you might have thought that the game was more in favor of player one, that player one had a better chance of winning, because they would win if the coin landed on H, J, or K. So it appeared that there were 5 outcomes that favored player one versus only the 2 I's that favored player two. But that would be true only if this was a simple experiment. The fact is, this game hinged on what we call a complex experiment. Consider the simple experiment. What if we took all 7 of these letters, and they were like Scrabble tiles that we threw into a bag? We shook it up and we're going to randomly select one. If we were to select an H, J, or K, then player one would win. Well, then it would be true that they had a 5 out of 7 chance of winning, whereas player two would only win if we selected an I. Seeing that there are only 2 I's in the bag, they would have a 2/7 chance of winning. So our thought that the game is more in favor of player one would be true. But as I said, this game does not hinge on a simple experiment. It is tied to a complex experiment. A complex experiment are simple experiments strung together. A simple experiment is selecting 1 tile. Complex would be selecting 2. A simple experiment is flipping 1 coin. A complex experiment would be flipping 2 coins, or 3 coins, or 4 coins. Again, a simple experiment would be rolling 1 die, but a complex experiment would be rolling 2 dice and considering what came up on both of those as our final outcome. So this game, because the direction of the coin was tied to what turned up on each of the 3 coins, this game is actually tied to a complex experiment. Now, sometimes coming up with all the possible outcomes in a complex experiment can be a little bit tricky. Consider the simple experiment of flipping 1 coin. If I said we were going to flip 1 coin, I have no doubt that all of you would be able to tell me that the possible outcomes would be heads or tails. Let's say we were going to look at flipping 2 coins. I think most of us in our head can think about all the possibilities that could turn up on both coins and the resulting outcomes. For example, if we flip 2 coins, perhaps we could get a head on the first coin with a tail on the second coin. We could get a tail on the first coin with a head on the second coin. Or perhaps both turned up tails, or both turned up heads. It's relatively easy to keep track of all of those in our head, jot them down, and be fairly confident that we got all of the potential outcomes. But as the complexity of the experiment increases, so does the size of the sample space. And generating that sample space, all the possible outcomes, generating that in our head can be much more challenging. Our experiment didn't consist of flipping 1 coin or even 2 coins. It actually was tied to flipping 3 coins. Now, some of you may be able to think about those 3 coins and all the possible combinations that could turn up with all 3 of those coins. Many of us, though, are going to find that a little hard to do. And even if we did list out all the outcomes, we might be a little hesitant to say that we got all of them. We might not be 100% sure. So one thing we can do is use a tool to help us generate our sample space. And the tool we're going to use is something called a tree diagram. What the tree diagram does is it lists all the outcomes for each stage of the experiment. Each stage is the simple experiments that have been strung together. At the same time, it will tie back to the previous outcomes that occurred in any stages before it. So let's get started and take a look at what a tree diagram would look like for our game. Remember, the first coin we were considering was the penny. If you flip a penny, the only 2 outcomes would be heads or tails. Okay. Now what we'll do is consider the nickel, and we'll list the outcomes for the nickel, but we'll tie it to what could have come up on the penny. Meaning, right here is where we have a head on the penny, but we know on the nickel it could have turned up heads or tails. However, we know that maybe the tail turned up on the penny, but if you flip a nickel, the only thing that could turn up is heads or tails. Now, if you read along the branches right here, this is what we would get if we only flipped 2 coins. So we have head, head. There's that outcome. You have the outcome of head, tail, which we listed right here. You have the outcome of tail, head, which we have listed here. and we have the outcome of tail, tail, which is listed right here. So you can see that our tree diagram actually helped us generate all the possible outcomes for the complex experiment of flipping 2 coins. Okay, but our game was tied to flipping 3 coins. So we need to take this a step further and branch out yet again. So we have to take into consideration what could turn up on the dime at each of these points. Well, of course, if a head turned up on the nickel, you could get a head or a tail on the dime. But if the tail turned up on the nickel, you could get a head or a tail on the dime. But wait a minute, these two outcomes, or these outcomes that we just generated were all for if the penny turned up heads first. We have to take into consideration what could happen if the penny turned up tails first. So again, branching out, here's the head on the nickel with a head or a tail on the dime. Here's the tail on the nickel with the tail on the penny and a head or a tail on the dime. Now at this point, we can read along the branches and we will see the outcomes, the final outcomes for flipping all 3 coins, the penny, the nickel, and the dime. So here we have head on the penny, head on the nickel, head on the dime. What I'll do is I'll list the outcome at the end of those branches so I know that I followed that path completely. Remember, we could have had a head on the penny with a head on the nickel, but a tail on the dime. So that would result in head, head, tail. Still starting with the head on the penny, we could have had a tail on the nickel and followed up by a head on the dime. So head, tail, head. Finally, with the head on the penny and a tail on the nickel, it could have been a tail on the dime. So head, tail, tail. Keep in mind, though, that the head might have never turned up on the penny. It could have been the tail. And as we read along the branches here, we see that we could have the outcome tail, head, head. Here to here to here gives us tail, head, tail. Tail on the penny, tail on the nickel now, with a head on the dime, gives us tail, tail, head. And finally, a tail on all 3 is definitely a possibility. Now, these are all the possible combinations that we could get given that we flip 3 coins. We now need to look at these outcomes and see what that means for our game. Look at something like head, head, head. Our coin starts on H, and heads move the coin to the right, so that would be right, right, right. That lands on K, and that means that player 1 would win. Consider, though, the next outcome. That's the outcome of head, tail, or excuse me, head, head, head. Okay, well, again, we start on head, or on H. Head moves it right, head moves it right again, but that tail moves it left. This outcome right here gives us an I, and that's when player 2 would win. Looking at the next outcome of head, tail, head, okay, keep in mind that our coin always starts out on H. So if we're considering this outcome, head, tail, head, we go right, left, right. We are back on I again, and that is when player 2 would win. Okay, we have to consider this outcome, head, tail, tail. Well, again, our coin starts out on H. Head, tail, tail, moves it right, left, left. We're on I again. Happens to be the other I, but there we are. Player 2 wins again. The next outcome of, let's see, tail, head, head. We start here. Tail moves it left, tail moves it left, but that head moves it right, and we are back on I. Player 2 wins again. Tail, head, tail is the next outcome. I bet you can guess what's going to happen here. Tail, left, head, right, tail, left, I again, player 2. Tail, tail, tail is going to make our coin move left, left, right. We are on I again, player 2 wins. It's not until we get to our final outcome of tail, tail, tail that we finally see left, left, left. We land on K, and that means that player 1 would have a chance of winning. So whereas we thought the probability of player 1 winning was 5 out of 7, if we look at it and consider it as the complex experiment it is, we see that the probability of player 1 winning is actually only 2 here, and here out of the 8 outcomes. Player 2, the probability of player 2 winning is 6 out of 8. So it's actually a 25% chance that player 1 wins versus the 75% chance that player 2 wins. And now we can see exactly why player 2 had the advantage in this game. In the next video, we're going to look at a counting example for counting elements, the total number of elements in multiple sets.